Welcome to the Deep Dive. We're diving deep into adversarial machine learning today, specifically attack and defense strategies.
Sounds intense.
It is, and we've got a great source, a 2023 research paper by Wang and their team.
Oh, yeah, I know that one. Adversarial Attacks and Defenses in Machine Learning-Powered Networks, a Contemporary Survey.
That's the one, a real goldmine, even if you're already familiar with the field.
Definitely. It covers the latest in adversarial attacks, particularly in network communications, finance, autonomous driving, areas where the stakes are high.
Yeah, the real-world impact is what really grabbed me, like that example of manipulating Wi-Fi signals.
To deceive human activity recognition systems.
Exactly. Imagine the privacy violations if an attacker could do that.
Chilling thought, and it doesn't stop there. The paper also talks about the dangers for autonomous vehicles.
Oh, right. Even something like a sticker on a stop sign could lead to misclassification.
With potentially catastrophic results.
And we can't forget about finance. Algorithmic trading systems could be manipulated too.
Leading to massive financial losses, it really underscores the need for strong defenses.
Absolutely. So how do we even begin to understand these defenses?
Well, the paper breaks down the attack landscape in several ways.
Okay, like what?
We've got digital, physical, and cyberspace attacks, each with their own characteristics and, implications.
So digital attacks directly manipulate data, while physical attacks involve something tangible.
Like that sticker on the stop sign, right?
Exactly. And cyberspace attacks target systems in the digital realm, disrupting networks and sensor data.
Right, and then there's the classic white box, black box, and gray box attacks.
The attacker's knowledge of the target model.
Exactly. White box attackers have full knowledge. Black box only see inputs and outputs, and gray box are somewhere in between.
Makes sense, but the paper goes deeper than those traditional classifications, right?
Oh, yeah. It dives into more nuanced types, especially in how they exploit the training process of machine learning models.
Interesting. So let's get specific. What about gradient-based attacks?
Those exploit the way models are trained using gradient descent. They craft perturbations to force misclassifications.
I see. And what about those Lafayette and DSNGD techniques I saw mentioned?
You're getting into the specifics now.
They got my eye.
Right. Lafayette, or latent feature attack, targets those hidden features during gradient descent.
So it's more efficient?
Computationally, yeah, it leverages those features that aren't directly observable, but still influence the model's decisions.
Clever. And what about DSNGD?
Dynamically sampled non-local gradient descent.
Catchy name.
It focuses on efficiency too, but by streamlining those computationally intensive sampling operations.
So as models become more complex and data sets larger, attackers need to be more efficient.
Exactly. Now, moving beyond gradient-based attacks, there are also constrained optimization-based attacks.
Constrained optimization.
The goal there is to find an adversarial example that maximizes misclassification, but with constraints.
Constraints on what?
On how much the input can be modified. The paper mentions GF attack as a key example.
Okay.
Generalized adversarial attack framework, it targets graph embedding models.
Interesting. And it doesn't need labels or predictions.
Making it applicable in a lot of graph-based learning scenarios.
Okay, so we've got gradient-based and constrained optimization-based attacks. What else?
Well, there are also gradient-free or heuristic attacks.
Heuristic meaning?
They use search algorithms or decision-based techniques to find vulnerabilities without relying on gradient information.
So a different approach altogether.
Right. One example is the attack on attention, or AOA.
AOA. What does that target?
The attention heat map, instead of directly changing the output, it tricks the model into focusing on irrelevant features.
So it misclassifies because it's looking at the wrong things.
Exactly. Now, get this. There are also these visually striking adversarial patch attacks.
Adversarial patches like stickers or something.
Kind of, yeah. You can actually fool real-world machine learning systems with carefully designed patches.
So a sticker on a traffic sign could cause an autonomous vehicle to misread it.
That's the idea. The paper talks about RP2 and PSGN as specific patch attack methods.
Okay, break those down for me.
RP2 stands for robust physical perturbation. It creates those perturbations that are resilient to different physical conditions.
Like different angles and distances.
Exactly. And PSGN, the perceptual sensitive generative adversarial network.
Another catchy name.
It focuses on making the patches visually plausible so they're hard to detect.
So they exploit our own perceptual biases.
Precisely, making them even more effective.
Okay, so we've covered a lot on the attack side, but what about defenses? How are researchers fighting back?
Well, the paper gets into a whole range of strategies, from classic approaches like adversarial training to more specialized techniques.
Wait.
Things like adversarial sample detection and robustness enhancement through regularization.
Okay, so let's unpack those, starting with adversarial training. What's the basic idea there?
It's like fighting fire with fire. You train the model on adversarial examples so it learns to resist them.
So you're basically exposing it to those malicious inputs during training.
Right. The idea is to teach it to distinguish between legitimate and malicious data points.
Makes sense. The paper also talks about adversarial sample detection.
Right. Building systems that can flag potential adversarial examples before they cause problems.
Like a security system for your AI?
Exactly. One example they mention is LID and CD for radio signal classification,
LIB and CD.
local intrinsic dimensionality, and constellation diagram.
Okay, and that analyzes radio signals to detect anomalies.
Right. It looks for patterns that deviate from what's expected, which could indicate manipulation.
So it's not just about the data itself, but the underlying structure and patterns.
Precisely. Now let's move on to those techniques that enhance robustness, making the model less susceptible to manipulation.
Okay, and regularization plays a key role there, right?
Absolutely. Regularization involves modifying the training process or the model's architecture to make it more stable.
So less sensitive to those subtle adversarial tweaks.
Right. The paper dives into various techniques categorized by where they're applied input, middle, or output layers.
Okay, let's start with the input layer. What's happening there?
At the input layer, the focus is on pre-processing the data to mitigate the impact of adversarial noise.
So cleaning up the data before it even reaches the model.
Exactly. Things like noise reduction techniques come into play.
Like what specifically?
The paper mentions JPEG compression and median filtering to smooth out those subtle perturbations.
Interesting. So it's like filtering out those adversarial manipulations.
Right. And another approach is to project the data into a different feature space.
A different feature space.
Yeah, where those adversarial perturbations might be less effective.
Clever. Are there specific techniques for that?
They mention PCA, principal component analysis, and wavelet transformations.
So you're changing how the data is represented to make it harder to manipulate.
Exactly.
This is all fascinating, but I think we need to pause here.
Yeah, we've covered a lot.
In the next part of our deep dive, we'll explore those middle and output layer regularization techniques and how they contribute to building more robust models.
Sounds good. So we were talking about regularization and how it's applied to those middle layers of a neural network.
Yeah, those middle layers are where the model really learns those complex representations, right?
Exactly, and that's why they're so susceptible to attacks too. The paper highlights some techniques to make them more resilient.
Resilient, like how? What kind of techniques are we talking about?
Well, one prominent one is ANP,
ANP.
adversarial noise propagation.
So instead of just cleaning up the input data, we're actually adding noise.
Yeah, to the hitter layers during training.
Interesting. So by making the model deal with this internal noise, it becomes less sensitive to those adversarial perturbations.
It's like giving it a workout, making it stronger.
I like that analogy, but the paper mentions something strange. Adding noise to those shallow layers, the ones closer to the input, can actually hurt robustness.
Yeah, it's a bit counterintuitive, right? More research is needed there, but it seems those early layers are more vulnerable to the negative effects of noise.
Makes you wonder about the way information is processed in those layers.
Definitely highlights the delicate balance we need to strike.
So ANP is one technique.
Yeah.
What else is there for those middle layers?
Well, there's also DHAT, dual head adversarial training.
Two heads.
Yeah, basically you add a second head to the network at an intermediate layer.
So it's like a second brain.
Kind of. It learns to classify the data independently, giving a second perspective.
So instead of just one pathway for decision-making, there's internal competition.
Exactly. And during training, the outputs from both heads are combined, forcing the model to learn more robust representations.
Interesting. So by having those two perspectives, it becomes less likely to be fooled by an attack.
That's the idea. Now let's shift gears and talk about the output layer.
Okay, so how does regularization work differently at the output layer?
Well, at the output layer, the focus is often on manipulating the decision boundary or refining the loss function.
Right. The decision boundary is what separates the different classes in the model's output.
Exactly. So by manipulating that boundary, you can make it harder for adversarial examples to cross over and cause misclassifications.
Okay, and what about those loss functions?
The loss function tells the model how to measure its errors. So by carefully designing it, you can encourage the model to learn representations that are less susceptible to manipulation.
So it's like giving the model the right incentives.
Exactly. One technique mentioned is adversarial margin maximization networks, or AMM.
Yeah.
It tries to push that decision boundary further away from the data points, creating a larger margin of safety.
Like building a wider moat around a castle.
Exactly. Another strategy is distillation.
Distillation. Like with alcohol.
Not quite in this context, it means training a smaller student model to mimic a larger, more robust teacher model.
So it's like passing on the knowledge and resilience to a smaller, more efficient model.
Exactly. Techniques like knowledge distillation or KD and AGKD-BML fall under this category.
AGKD-BML.
Attention-guided knowledge distillation and bidirectional metric learning. It uses attention mechanisms to guide that distillation process.
So even in distillation, attention plays a crucial role.
It seems so. The paper also mentions some specific loss function designs for enhancing robustness at the output layer.
Okay, like what?
Well, there's the bounded logic function, or BLF, and polyhedral envelope regularization, or PER.
Those mouthful, what makes them unique?
BLF constrains the model's output logics, preventing those extreme predictions that adversarial examples often exploit.
So it's like setting limits on how confident the model can be.
Right, and PER uses a more geometric approach, creating a polyhedral envelope around the data points that the decision boundary can't cross.
So it's like a geometric constraint.
Exactly. Now, remember, we've been categorizing these techniques by layer, input, middle, output, but some approaches aim to enhance robustness across all layers.
Oh, interesting. Like what?
Well, one concept is gradient masking.
Gradient masking. What's that all about?
It's about hiding the model's true gradients from attackers.
Okay.
Remember, those gradients are often the key to crafting those adversarial perturbations.
So by masking the gradients, you're making it harder for attackers to find the vulnerabilities.
It's like hiding the model's blueprints.
I like that analogy. So techniques like defensive distillation and certain types of adversarial training use this gradient masking.
Right, they create a smokescreen to obscure the model's inner workings.
But the paper suggests that gradient masking might not be foolproof, especially against black box attacks.
Right, because black box attacks don't need those internal gradients. They work by observing inputs and outputs.
So they can find vulnerabilities regardless of the gradient information.
Exactly. It shows that gradient masking, while effective in some cases, might not be enough.
So we need a diverse set of defense strategies, each with its own strengths and weaknesses.
Absolutely. And the paper does a great job outlining the challenges that remain.
Challenges like?
Well, transferability, for one.
Meaning an adversarial example designed for one model might also work against another.
Exactly. It's a major headache for defenders because even if you make your model robust against one attack, it might not hold up against others.
So how are researchers tackling this transferability problem?
One approach is to use ensembles of models, combining the predictions of multiple models, each with its own strengths and weaknesses.
So it's like having a panel of experts making the overall decision more robust.
Exactly. And there are other strategies being explored, like robust optimization methods or introducing randomness into the model's architecture.
So making it harder for attackers to predict the model's behavior.
Right, but transferability remains a big challenge.
Look, so transferability is one challenge. What else?
Well, scalability and generalizability are major concerns too.
Right, because a lot of these defenses work well in research settings, but scaling them up to real-world applications with massive data sets can be tough.
Absolutely. And generalizability is about making sure those defenses work across different types of models and tasks.
So we need solutions that are broadly applicable, not just specific to one attack or model.
Right. It's about building a flexible and adaptable defense system that can evolve with the threats.
And there's another limitation we talked about before: data dependence.
Yeah, a lot of these techniques rely on having tons of training data, including those adversarial examples themselves.
But in the real world, we might not always have that data, especially with new threats.
Exactly. It highlights the need for more data-agnostic approaches.
So it seems like we're still in the early stages of understanding this whole adversarial machine learning game.
In some ways, yes, but the research is moving fast.
So a sense of cautious optimism is warranted.
Definitely, the paper, while outlining the challenges, also showcases the progress being made in developing more robust and secure machine learning systems.
So what's next for our deep dive?
Well, in our final part, let's synthesize the key takeaways from all this and explore what it means for the future of machine learning.
So much to unpack from this paper.
It really lays out the landscape, huh? Both the threats and the defenses.
It's like a constant arms race, isn't it? Attackers finding new ways to exploit things and defenders scrambling to keep up.
And it's not just a theoretical problem anymore. Those real-world examples really hit home.
Yeah, the stakes are getting higher and higher.
Exactly. So, for our listeners out there who are already deep in this world, what are the key takeaways from this paper?
Well, I think the first thing is just how broad this attack landscape is becoming. It's not just images anymore. It's networks, finance, autonomous systems, even radio signals,
Right. Any system that uses machine learning is potentially vulnerable.
and the attackers are getting more clever too. Those gradient-based attacks, constrained optimization attacks, gradient-free attacks, those adversarial patches. It's a whole toolbox of tricks.
And on the defense side, researchers are coming up with some pretty ingenious countermeasures.
Like that adversarial training you mentioned, where you basically fight fire with fire.
Exactly. And then there's SAML detection, trying to catch those adversarial examples before they do any damage.
And all those regularization techniques to make the models more robust.
It's a multi-pronged approach, for sure.
But as we've talked about, there are still some big challenges.
Yeah, transferability, scalability, generalizability, and data dependence are all major hurdles.
We need defenses that can adapt to new threats, that can scale to real-world data sets, and that don't rely too heavily on specific data.
It's a tall order, but the research is moving fast.
It feels like we're just scratching the surface here.
We are, but that's what makes it so exciting, right? There's so much more to discover.
And for our listeners out there, keep exploring this research. Dive deep into the specific techniques and think about the implications of these advancements.
Because the future of machine learning depends on our ability to stay ahead of these adversarial challenges.
To build AI systems that are not only powerful, but also secure and trustworthy.
So keep questioning, keep innovating, and keep pushing the boundaries of knowledge.
That's a great note to end on. Thanks for joining us on this deep dive into adversarial machine learning.
It's been my pleasure.